After we install and download Anaconda, we can start Anaconda Navigator, and from there we can launch Jupyter Notebook. So I'm going to press the launch button now. It'll pop up a browser window showing us what it can see in Jupyter. Now this is the root of my computer, and in Documents, Mech 241, I've got some of the files I'd like to work on. So I'm moving over to find the files that I'm interested in. They're in Module 1, and they're in here under Juicebox. And we're going to use this Python notebook called juicebox.ipynb in order to understand the idea of how Jupyter works. So far we've just been browsing, we found the file we're interested in, and I'm going to click on it to open it up. It loads in, and we see in our view in our browser multiple different cells. So this is a cell here, this is another cell, and another cell. So we've got multiple cells. If I go to this particular cell at the top, we can see that it's mostly just text explaining what's going on. And if I double click on it, I'll see it in a slightly different view. Now this is a markdown cell, and what that means is that it's got basically text and stuff in it that we'd like to be able to see what we're looking at. So now that I've maybe edited this cell, I can go back and hit the play button to execute that cell, and it formats it according to the markdown commands. We'll do some more about that later. This next cell is a couple of lines of Python code, and it's going to import the numerical Python elements as NP, and it's going to import some stuff also from the math library. So we run that. This cell is another Python cell, and it's got another import here to import some stuff that can display video, and it's embedding actually the YouTube video that we saw out in OnQ that includes this Juicebox experiment. So if I run this one, it goes out and actually finds the video, and we could play the video inside this video and see what's going on. But for now, I'm going to skip that. I'll pause it, and I'll just go back to the beginning or somewhere around here where we can see the juice box. Now we're doing this viscosity test with a straw, and the rate at which the fluid is coming out depends on the friction on the inside of the straw and also the size of the potential energy that we've got available under gravity to drive the flow through that straw. So looking down here, we've got a schematic picture of that. We've got a juice box, which is more or less rectangular, A wide by B long, and the straw is a distance C under the water. So whatever liquid we put in here, the volume of liquid that's going to be in here that has to drain out through the straw before the bubbles show up is going to be A times B times C as a volume. It'll be coming out of the straw at some velocity V, an average velocity, and that'll let us figure out what the flow rate is. And the straw is L long, so the length of that straw, the longer it is, the more friction there's going to be on the inside of the straw, and also the longer the distance from the surface here down to the exit here, which can be available as potential energy to drive the flow. So if we look at our VPIG's mnemonic, viscous forces, they're going to be important for the friction on the inside of the straw. The pressure is the same on all sides. It's atmospheric pressure. It might be a little higher in the middle of the juice box, but it's only due to gravity and hydrostatics, so we're not going to worry very much about pressure. Velocity is changing significantly. It's 0 here. It's accelerating into the straw and coming out of here at some noticeable velocity unless the viscosity is really high. Gravity, well, gravity is what's driving the flow. If we didn't have any gravity, the liquid would just stay here in the juice box. Surface tension, it has a minor effect. We're going to ignore it in this analysis. It will show up a little bit in the curvature down here at the exit from the straw, but we'll concentrate on the big things, which are going to be the inertia, the viscous forces, and the gravity that's contributing to both the acceleration of the flow and working against the viscous forces. So I'm doing all of this in MKS units, meters, kilograms, seconds, so that all of the units will be consistent. So I measured and I found that A was about 4 centimeters, B about 5 centimeters, C about 4 centimeters in my example, and the inside diameter of the straw was about 4 millimeters. The length of the straw, 8 centimeters, and gravity, 9.81 meters per second squared. So the difference in height that's driving the flow, well, when it's full, it's C plus L, and when it's almost empty, it's just L. So on average, it's about half C plus L. So that's the average change in elevation driving the flow. And we're not going to worry about keeping track of the fact that we've got a whole variation across here. We'll just do it on an average basis. We've got two cases that are the limiting cases. One is if we had no friction. So all we'd be doing is using that potential energy to accelerate the flow. And from later on in Module 5, we have Bernoulli's equation, which will tell us the relationship between the kinetic energy here and the potential energy due to that change in height under gravity. And that'll give us a way to calculate the velocity if we just had the inertia being important, no friction being important. So don't worry too much about what's behind this. Just recognize that this is kinetic energy and we're turning all the potential energy into kinetic energy, and that gives us this equation if we only considered the inertial forces. The other case, if we had no inertia, if we only had frictional forces, then we'd have to look at the potential energy, this delta Z, divided by the frictional energy, this 32 mu L over rho G D squared. And that's a little more complicated. You're going to see that in Module 6. But let's just take it for now that what we're doing here is we're saying that the frictional dissipation due to viscosity has to match up exactly with the potential energy. So we're using all of the energy to overcome the friction. And that'll have a velocity associated with a purely frictional system that we can get from this equation here. So if we knew the fluid properties, we could make a prediction of the velocity. The fastest it could be coming out is the no friction case. If we had no friction, then we'd get as fast a value as we possibly could. So here I've just taken this equation from up here and I've typed it in to this Python cell down here, and now I can run that Python cell and see what value comes out. So if I hit the play button, whoops, I got an error. Why did I get that error? It says G is not defined. That's because up here, I didn't actually run that Python cell yet. So I run that Python cell, run that one, it reformats it. I get down here and I go to calculate that inertial velocity, and I get 1.4 meters per second. So let's just keep that 1.4 meters per second in mind. Now, the advantage here of doing this in Python instead of just doing it with your calculator, if it turns out that things changed and that was 5 centimeters instead of 4 because we'd mismeasured, I could calculate that over again. Why didn't I get a different value? Turns out, doesn't depend on that volume. That's going to come in later. But suppose I changed the length to 6 centimeters. And I did that velocity calculation again. I get a slightly different value. So the advantage of building this into a worksheet like this in Python is the same as building it into a spreadsheet. We've got multiple opportunities to go through and change things and see what happens. But let's go back and put that back to 8, which is what I actually measured. I get about 1.4 meters per second. And if the viscosity dominated, we'd be back to our frictional velocity, purely friction. And I can calculate that according to this formula. So I'll define what the viscosity is. This is the viscosity. This viscosity is about 10 times the viscosity of water. I'm just going to use this for an example. Might match up with our dishwashing liquid, for example. Density, around 1,000 kilograms per cubic meter. And we can get the kinematic viscosity as the ratio of the dynamic viscosity and the density. So now I can plug all of that into this equation. And when I go to run this code, I get an output velocity of about 0.6 meters per second. So less than half of what I had in the purely inertia case. So probably the inertial forces are not as important here, and our assumption that inertia is not making a significant contribution is probably okay. So now that we've got some ideas about how all of this works, these two limiting cases, let's go and measure what we actually got, because we checked out what the time was on our different measurements. So the volume flowing out is just A times B times C. We measured how long it took, that was time t, and so the average velocity is going to be equal to the volume that flowed out per unit time divided by the area of the straw. And if we divide that flow rate, the volume per unit time, by the cross-sectional area, we'll be using the same kind of conservation of mass that we'll get from Module 5, and we can figure out for what time we measured what the velocity must have been. So let's go down here, and let's start off by setting t just equal to 5. So if the time was 5 seconds, and the volume was A times B times C, and the area of the straw is pi d squared over 4, then we can get the velocity as the volume that's flowing per unit time divided by the area of the straw. And let's run our code here. So I get 1.273 meters per second. Let's call it 1.3 meters per second. That's almost as big as the entirely inertial assumption, so the one where we completely neglected friction. And what that's telling me is that for t equal to 5, the value we got for water, we're getting a flow velocity that's very much dominated just by the inertial effects. So the viscosity of the water is playing a very small role in what's going on. Now if I go back instead and make t an array, this illustrates some more strengths in using a Python script. If that's an array, let's try doing the same calculation with an array. And what comes out? We get 4 different values. So we still get the 1.3 meters per second for our time of 5 seconds for the water. But for 47 seconds, we get a velocity of around 0.13. For the 340 seconds, about 0.019, so way smaller. And finally, for the 20 seconds, the heated soap, we're in at about 0.3. So still much lower than the inertial velocity that we'd get if there was no friction at all. So although there may not be very much friction in this case with the water, there's a lot of friction causing the flow to be slower in here, and we can get some estimates of the velocity based on these, some estimates of the viscosity based on these calculated velocities. So let's combine all of these effects together to get a viscosity estimate. So remember, we were talking about the elevation change, the change in potential energy, having something to do with the change in kinetic energy. So we went from 0 up to having it moving. and the amount of energy that we're expending dissipating due to friction due to viscosity. Now we'll learn all about these in more detail later on in the course, but for now we can take this equation and rearrange it to get it in terms of the viscosity divided by the density, which is the kinematic viscosity. And if we know delta Z and the velocity, g, the size of the straw, the length of the straw, and again the velocity that the fluid's traveling at, we can figure out what this kinematic viscosity is based on our measurements. And if we do that, here I'm going to calculate the kinematic viscosity based on this equation up here. So this is just the same equation, delta Z minus the measured velocity squared divided by 2g times g times d squared divided by 32 divided by L divided by the measured velocity. Then I can print that out and see what values I get for viscosity. So let's check it out. When I do that calculation, I get these numerical values. And so for the water case, that was the 5-second case, I get 8.4 times 10 to the minus 7. That's pretty close because the actual value for room temperature water is about 10 to the minus 6. So that's off by 10 or 15%. That's pretty darn close. For the next one, the dishwashing liquid at the regular temperature, or sorry, no, this is canola oil at the regular temperature. I get canola oil having a viscosity of about 4.5 times 10 to the minus 5. That makes it about 40 times more viscous than water. And then for the cold dishwashing liquid, I get a viscosity of about 3.3 times 10 to the minus 4, making it a factor of almost 10 again more viscous than the canola oil. So I've got some measured viscosities here, and I can go and look up and see if those viscosities match up with what I know from my research on the web.